Hello everyone, I'm Hao from UPenn. I'm sure you have seen lots of 3D reconstruction with cameras and lidars, but what I'm going to talk about is to reconstruct a hidden scene around corners. This is joint work with Zitong and my advisor Mingming. Perception and reconstruction are essential for mobile robots and other autonomous systems, but even with the latest camera and lidar-based perception methods, is that truly enough for safe autonomy in cluttered environments? Unfortunately, it's not. These sensors can only perceive objects that are within direct line of sight. However, wireless sensors such as radars have the potential to see around corners. Because radar signals have a much longer wavelength, common surfaces like walls behave specularly like mirrors. As a result, signals bounces in predictable paths and the returning IF echo carry rich spatial information for the non-line-of-sight 3D reconstruction. However, this task is challenging. First, unlike LiDAR, which produces clean and accurate point clouds, radars has a fundamental limitation in sensing resolution. Second, due to multiple times of reflections, hidden structure and objects showed up in mirror positions that are hard to be interpreted. Together, these challenges interact with each other and make it difficult to learn a full 3D scene directly from the radar signals. To solve this problem, we designed a two-stage pipeline that separates imaging from mirroring correction. In the first stage, we interpret the radar signal. We use an imaging model to extract both direct and hidden geometry from the IF heat map. This gives us range images that show the total travel distance for each bounce. With these images, we have both line-of-sight and non-line-of-sight points, but they appear at mirror locations. Then, for the second stage, we perform spatial reasoning. The model determines the true position of these mirror points and refines the 3D scene. Specifically, we designed a shared encoder but separate decoder structure for our multi-return IF imaging model. The encoder processes the full heat map and extracts a unified set of RF features. Then, each of the decoders specializes in predicting the range image for its corresponding return. Since each of the return comes from the reflection of the geometry in the previous one, it shows a mirrored representation of the environment. To build a real 3D scene, we draw inspiration from how signals physically reflect and trace this process. Here is how it works. We use a ray tracing module to track how the signal travels and updates where it hits, which helps us recover the real geometry. The track locations are then used to determine the reflection path of the next return. By cascading these ray tracing modules together, the reconstruction gradually reveals the hidden non-line-of-sight regions. It's worth noting that our ray tracing module does not purely rely on physical modeling. Instead, it combines signal processing and learnable layers by using hybrid estimation blocks. These blocks improve the surface normal and the direction reflection estimation to mitigate error accumulation during ray tracing. Here is our system. We use a motor to rotate the radar among the sensors on the mobile robot. For experiment setup, a person is standing in non-line-of-sight region around the corner where the robot cannot see him. To test our system, we collect a dataset in diverse scenarios. Here are the multi-return imaging results. In the first return, the person is not visible because they are in non-line of sight. But in the second and third returns, the person becomes clearly visible. Baseline methods, on the other hand, reconstruct the scene incorrectly. This is another example where baselines show several artifacts. Here we present the final scene reconstruction results with both mesh and point cloud, where hidden structures and humans are clearly recovered. This is another example. Here is a video of a static human and a moving robot. We show the multi-return imaging result. And this is the final reconstruction result. Now we show another case where the robot is static while the human is moving. For more information, please visit our website. Thank you.